All right, everyone. Welcome to lesson 17 for the semester. So last time we got acquainted with what were called series, i.e. where we took one of those infinite lists of numbers or sequences and we added up all of the numbers in the list. Now, last time we talked about what converging and diverging meant, and then we started to learn about convergence test by talking about the test for divergence. So what we're going to do today is we're going to talk about series where we can find the actual sum of the series. So we add up all the numbers and we know what specific number it adds up to. Now you might be like, oh, well, hopefully we could do that with every series that converges, right? Well, unfortunately, that's not the case. If most series that we look at, we could tell if they converge or diverge, but we can't, or sorry, we just don't know what they sum up to. It's actually pretty hard to find the sum of the series. Kind of like it's hard to do kind of like how it's hard to do some integrals. So today we are going to talk about two series that you could sum up. So that's going to be today's lesson. Now, if a series that we give you is, if we ask you to sum it up, it's probably going to be one of these two series that we're going to talk about today. These are the only ones that we reliably know how to add up. So two types of series that are possible to find the sum of. The first one are going to be what are called geometric series. All right, so what is a geometric series? It's a series that looks like this. The sum from n equals some starting number a to infinity of c times r to the n. So we have some constant in here. Maybe that doesn't have an exponent, but we do have some fixed number and it's being raised to a power. So we're effectively adding up multiples of all of the different powers of this number, starting with whatever number this is right here. And this is a series where if it converges, we know what it's going to sum up for. Oh, the mic's not working? All right, let me fix it. All right, is that better? Is that good? Better? Okay, that's good. All right. So there's two types of things that can happen with this series. So if the absolute value of r, so the number being raised to a power, is less than 1, then the series converges. And moreover, it converges to the number cr to the a divided by 1 minus r. So it's going to go to this number specifically right here. So this is the number that's being raised to the power. This is the starting index of the number, which is usually 0 or bigger. And then this is the constant that we had. And by the way, I don't think I explicitly mentioned this last time, but you can move constants out of series with no issue. So this series right here is the same thing as if we just moved the constant out right there. Okay, now I said that that happens if the absolute value of r is less than 1, meaning it's between -1 and 1, not including the endpoints. But what if it's not? So what if the absolute value of r is greater than or equal to 1? Then the series diverges. And remember, when it diverges, it doesn't diverge to anything in particular. We just state that it diverges. Although in general, there are two ways you can diverge. You could diverge by going off to infinity, by becoming really large, or you could diverge by bouncing around, or possibly both, actually. There are occasions where we kind of flail wildly and go off to infinity and bounce around. But anyways, here, yeah, what's up?
You had said that it converges to CR to the A over 1 minus R.
Yeah, that's right.
Would it be A or would it be the same N that we got from the summation? Or is it something totally different? A different value?
Like this A?
Oh, no, I'm thinking of R to the N right above that.
Oh, so it's just whatever number is being raised to the nth power. That's the number that goes right here. And this
Okay.
A value is the first N value that we have in our series.
Gotcha. Thank you.
All right, so that's a geometric series, and we actually already have seen a geometric series before. We saw this one yesterday. The sum from n equals 1 to infinity of 1/2 to the n. Because remember, this was 1/2 plus 1/4 plus an eighth plus a 16th, and so on. So now what we could do is, since the absolute value of 1/2 is less than 1, we can use this formula to sum the series. So first of all, we check to see if there's a constant there, but there doesn't seem to be an extra constant at all. Then we have the number being raised to the n, so 1/2, and that's going to be raised to the a power, where a is our starting index. So it'll be 1/2 to the first power over 1 minus 1/2. Well, this ends up being 1/2 over 1/2, which will end up being 1 right here, which is exactly the same answer that we got previously. Now, the nice thing about this formula is that it works for any kind of geometric series, not just for this one right here. And I think we also saw, if I'm not mistaken, we took a look at the series for 2 to the n here. But this is going to be the sum of the powers of 2. And as you can see, these are getting larger and larger and larger, so this is going to diverge. So the intuitive reason as to why this is the condition here is that if you raise a number that has magnitude less than 1 to a power, like let's say 1/3, if you keep multiplying by itself, it's going to keep getting smaller, right? So like a third times a third will give you a ninth, and then a ninth times another third will give you 1/27, and so on. But if you take something with size bigger than 1, like say 3, you're going to have 3 times 3 is 9, and then 3 times 9 is 27. So those keep getting bigger. So that's why having the magnitude of the number being less than 1 will make it converge. And then we have the other situation where it'll diverge. And what about where it's equal to 1? What if we just sum up a bunch of 1s in a row? Well, that's not going to work either, because 1 plus 1 is 2, and then 2 plus 1 is 3. So that's just going to keep building on itself. And negative 1 to the n will keep bouncing around. All right. So let's take a look at an example we haven't done so far, or we haven't done last time. All right. So let's take a look at this series. The sum from n equals 2 to infinity of 3 over 2 to the n. So we first of all want to know if this converges, and if so, to what number? Okay. So let's see here. So I have a 3 up here that's not raised to a power, and I have a 2 to the n down here, so that is raised to a power. So what I'm going to do is I'm going to write this as 3 times 1/2 to the n. That's how I'm going to write it this time. And let's see here. Is this going to converge? Well, the absolute value of 1/2 is less than 1. So yeah, this is going to converge for sure. Now, since we know it's going to converge, we have our formula for what it's going to converge to. Our constant is 3, and then we do it times 1/2 raised to the starting index here. So that'll be 1/2 squared over 1 minus 1/2. All right, so let's see. On top here, we're going to end up getting 3/4. On the bottom, we're going to have 1/2. So then this is going to give us 3/2 if we simplify here. So we not only know that this series will converge, we know it will converge to 3/2. So if we add up all of the numbers in the list given by this formula right here, we're going to end up with 3/2. And again, I emphasize it's pretty uncommon to know exactly what a series will sum up to, although it is relatively easy to find out if a series will add up to something. So with geometric series, that's the exception. We can figure out what it adds up to. All right, let's take a look at another example of this. All right, let's take a look at something a little bit wilder here. On my original notes, I had 2020, but now it's 2021. So let's change it to 2021 to infinity of e to the 2n divided by pi to the n minus 1. Okay, so we definitely have something a little more complicated than what we had before. All right, now let's see here. Now, in order to get it, in order for us to see if this converges or not, we need to get it into the geometric series form. So we need a number times a number raised to a power. So let's see here. Let's see if we could try to get everything to be to the nth power. Well, let's see here. E to the 2n. Now, if powers are multiplied together, that means that we could write it like e squared raised to the nth power. Okay, so that's definitely a start. Now, I would like it if, is that an x on the bottom? No, it's a pi. Sorry. It's a pi. All right, now if I want this pi to be to the nth power too, so I can combine as a fraction. How do you think I can get this pi to be to the nth power? What can I do to get that to happen? Oh, yeah, that's a way of doing it. Pi to the n over pi. So we do that. So pi to the n minus 1 is the same thing as pi to the n divided by pi. Now, in order to get this improper fraction out of here, what we could do is multiply the top and bottom by pi. So those will cancel out, and then we just end up with a pi on top. So we have pi, and then we have e squared over pi to the n. And since everything is to the nth power right here, we can combine it into one fraction right here. All of it's raised to the nth power. All right, now let's think about this. Now we have this in the right form. This is our C right here. This is our R, and then this is our A. So let's see here. Absolute value of e squared over pi less than 1. What do you guys think about that? Is e squared over pi less than 1? No, yeah, pi is like 2.7 something. So if you square that, you're definitely going to be bigger than 3.1 for sure. So that's not going to be true. So this series diverges. Because what's going to happen is the numbers are going to keep getting bigger that we're adding up. So this is a number that's bigger than 1. If we keep multiplying by itself, it's going to keep getting bigger and bigger and bigger. Yeah. Yeah, sure. So the way exponents work is if we have anything to the a minus b, it's going to be pi to the a divided by pi to the b. So here we had pi to the n divided by pi to the 1, or just pi. Then I multiplied the top and bottom by pi, and then these two canceled, and I was just left with a pi on top right there. All right, so for all that work, we ended up just getting something that ended up diverging. All right. Does that a minus b work for all exponents? Yeah, that's right. It works for any. Yeah, so it doesn't need to be pi. We could have c to the a minus b is c to the a over c to the b like that.
Actually,
All right.
another quick question. You have e to the squared to the nth over pi to the nth. How did that simplify to e squared over pi to the n?
Because these were both to the nth power. So if you have two things that are both raised to the same power, you can combine them into one fraction.
All right.
Yeah, so what I'm saying is that a to the n over b to the n is a over b. All right.
Thank you.
All right, so I want you guys to give this a shot now. So why don't you guys try to do 5 times the sum from 1 to infinity of 2 to the n over 3 to the n minus the sum from n equals 0 to infinity of 3 over 2 to the n. And you could subtract series together. You simply figure out what this one converges to, figure out what this one converges to, and then subtract them. So why don't you go ahead and take a few minutes and look at this. Can I show the formula? Yeah. There it is. When we find out what it converges to, then multiply it by the constant. Yeah, that's a valid way of doing it. You can do it that way. One third, 4, 9. It seems like a lot of people think 4. A minute or two, we'll see if that's right. 7. Don't be afraid to stick up a minority of opinion. There have been a few times where the majority of people get something wrong and the minority gets it right. Yeah. Well, you could technically imagine it that way if you want to, because 1 to the n is 1. Yeah, because no matter how many times you multiply 1 by itself, it'll be 1. Give me another few seconds here. All right, let's go ahead and take a look at this. So I'm going to do each of these separately. So for the first one here, I have the sum from 1 to infinity, and this is technically 2/3 to the n. So absolute value of 2/3 is indeed less than 1, so this is going to converge. So if I use this formula up here to get what it converges to, I have the constant 5 times 2/3 raised to the first power over 1 minus 2/3. All right, so now it's fun with fractions time. So on the top, we have 10/3. On the bottom, we're going to get 1/3. So that means that this will end up being 10. All right, so this part of the series, this is going to sum up to 10 right here. All right, let's take a look at the this other part of the series. So this 3 doesn't have an nth power in it, so we can't do something similar to what we did here. So I'm going to move that 3 outside of the series. And now 1 over 2 to the n, that's the same thing as 1/2 to the n. All right, so then now we can use our formula. So we have minus 3, and then we have 1/2 to the 0 over 1 minus 1/2. All right, so what's this going to be? So we have 3 times 1 over 1/2. So this ends up being -6. So we combine 10 and -6, and we end up getting 4. for the whole thing. So the 4s had it. The 4s are totally right for this one. All right. So we got 4 from that. That's good. And that's geometric series in a nutshell. So this and like the previous problem are essentially as complicated as they get. Sometimes you need to multiply the top and bottom by something. Sometimes you need to factor something out or subtract. But most of the time it's not really too bad. Now I'll say this might be a little bit confusing. So one thing that will happen, let's say one of these diverged, but then the other didn't, what would happen? Well, then the whole thing would diverge. So if you want it to converge, you need both of the individual ones to converge as well. How is 2 to the negative n equal to 1/2 to the n? So we were talking about that actually in class a moment ago. So 1 over 2 to the n is the same thing as 1 to the n over 2 to the n. Because 1 and 1 to the n are the same because 1 multiplied to any power will just be 1. And then those can combine to be 1/2 to the n. So that's why those things are the same. All right, so that's geometric series. Now I want to talk about the other type of series that we're going to be able to sum up here. So series 2 that we're going to be able to sum up is called a telescoping series. It's kind of an odd name, and I'll explain where it comes from once we do one of them. So what is a telescoping series? Well, let's take a look and see. So for example 3, I want to find the sum of n equals 1 to infinity of 1 over n minus 1 over n plus 1. So I want to either find the sum or see that it diverges. All right, so maybe this goes off to infinity or bounces around. All right, so what I'm going to do here is this isn't a geometric series, right? Because we don't have anything raised to the n. The n's are actually in the fractions. They're not part of the exponent. So what are we supposed to do here? Well, what I'm going to do is I'm going to start plugging in numbers. So let's plug in n equals 1. So plug that into here and get 1 minus 1/2. Okay, well, that's not very interesting so far. Let's plug in n equals 2. Then I get 1/2 minus 1/3. And remember, all of these are being added together. Every n I plug in here is getting added together, the results. So that actually means that we have this negative 1/2 here and a positive 1/2. Those will cancel out. Now let's add in the n equals 3 term. So I have minus 1/3, or sorry, plus 1/3 minus 1/4. And then we could see that these will actually end up canceling out. And let's do one more for emphasis here. If I do n equals 4, I'm going to have 1 over 4 minus 1 over 5. And lo and behold, the 1/4 are going to cancel out here. So it seems like every step of the way here, I'm always canceling something out, but there's something I'm never going to end up canceling out. And what's that? What term is never going to go away? It's that first term, right? It's 1, because these denominators keep getting bigger, right? So there's no way it's going to wrap around and come back to having a 1 down there. So this 1 is here to stay. Now, also at every step of the way, I have something else. I always have minus 1 over something. So let's see what the pattern with that is. So let's say I get down to some number big N, right? Then we have 1 over big N minus 1 over big N plus 1. Now, presumably on the previous step, this would have canceled with something up here. So then I'm just left with this. So it seems like my nth partial sum, meaning where I add together the first n terms, so this big N, will be 1 minus 1 over n plus 1. It's not just going to be 1 because we always seem to have this little leftover part that kind of comes with us every step of the way. But the nice thing is that leftover part is having an increasingly large denominator. Now, this is the partial sum, right? This is the nth partial sum. Now, remember what a series is. A series is simply the limit of the partial sum. So a partial sum is a running total, and if we send that running total to infinity, then we're going to get all of the terms. So if we look at the limit as n goes to infinity for this, that's going to give us the sum of our series. All right. So now what is this limit going to be? Well, we have 1 minus 1 over something getting huge. That's going to be 1. So that's going to be the sum of our series. All of this stuff is going to end up being 1 right here. All right. Now, why is this called a telescoping series? What on earth does a telescope have to do with something like this? Well, you may remember kind of those old-timey telescopes that maybe someone like Galileo or maybe like a pirate captain or someone might use. They had the kind of collapsible telescopes where they were able to kind of, they had a bunch of segments and they kind of pushed it in until it's simplified down to just one thing. That's where that name comes from. Yeah, it's exactly like that. Yeah, right. Yeah, so you see, kind of just crush in all of the segments until you have just one left. All right, let's take a look at another example of this. It'll be a little bit different. This time, let's take a look at the sum from n equals 1 to infinity of sine of n minus sine of n plus 2. Okay, now this one looks pretty different from the previous one, but there is one thing that they have in common, and that's they have two of the same type of function, with the only difference being what you're adding to the n. So here I have 1 over n, and here I have 1 over n plus 1. Here I have sine of n, and here I have sine of n plus 2. So it's the same function being subtracted, just with a slightly different input. That's a really good sign that you have a telescoping series. All right, so let's write out the first few terms of this one and see what's going on. All right, so let's do 1. So we have sine of 1 minus sine of 3. Okay, that's not really telling us anything yet. Here we have sine of 2 minus sine of 4. Still no canceling there. Now we have sine of 3 minus sine of 5. And finally, we start to see some kind of canceling here. We have negative sine of 3 here and positive sine of 3 here. Then we have n equals 4. And what happens with that? Well, we have negative sine of 4 here and sine of 4 there. With n equals 5, we have sine of 5 minus sine of 7. Those will cancel away. So it seems like the only difference between this one and the previous one is that we're canceling with something that happened 2 terms back, not just 1. And usually the difference between these, so the difference between n and n plus 2 is a size of 2. That'll be how many rows you have to go back to see it repeat. So since the difference between these inputs is 2, we have to go back 2 rows to get our cancellation. All right, now I'm going to do one more for emphasis, and then I think we'll be able to see the pattern pretty clearly. So we have sine of 6 minus sine of 8. So those will go away. All right, now it seems like every step of the way, we always have these guys up here at the front. We always have sine of 1 and sine of 2, right? So those don't seem like they're going anywhere. And then it also seems like we have these 2 signs of large numbers down here at the bottom. All right, so let's see if we can find the general pattern for this. So let's say we go out to a big N, and we have sine of n minus sine of n plus 2. And on the previous row, we would have sine of n minus 1 minus sine of n plus 1. All right, so what's going to happen is these are going to cancel with stuff that's happening up here, and we're going to be left with these 2 right here. Can I go up slightly? Yeah, sure. Here we go. All right, so this means that our partial sum is going to be sine of 1 plus sine of 2 minus sine of n plus 1 minus sine of n plus 2. Right there. All right, so this is our partial sum. Which ones are crossed out? So I'm imagining that we skipped a bunch of them, and then we're crossing out with the sine of n and n minus 1 that happened right before these right here. Another way to do this, another way to get this general pattern, if you don't like thinking about it this way, is we could stop at a certain point and then pay attention to what the numbers are that are left over. So for example, if we stop at n equals 6, we see that we have a 7 and 8 left over. So that's going to be an n plus 1 because this is 1 bigger than our n, and this will be an n plus 2 because this is 2 bigger than our n. So that's another way of getting this if you don't want to do it this way. All right, so now we have our nth partial sum. Let's look at the limit as n goes to infinity of this, and that will give us the sum of our series. So it's kind of tempting based on what we saw last time to just say, oh, it's going to be sine of 1 plus sine of 2. But the problem is that we have these guys at the end here. And the thing about sine is it doesn't decay to 0 like what we had in the previous problem. Sine is just going to keep bouncing around in between -1 and 1. So these numbers right here combined, they could be anywhere from -2 to 2, no matter how far we go out. So we have these numbers right here, but then we keep having this tail that just keeps oscillating between -2 and 2. So what do you think we could say about this limit here? Yeah, the limit's not going to exist. So the limit's not going to exist, meaning that the series diverges. And since these didn't go off to infinity, this will end up being one of those limits where, or sorry, one of these series where the terms just kind of keep bouncing around and they don't really settle down to anything. So in this case, even though we had a telescoping series, it doesn't necessarily mean that everything is going to work out and converge. We could still have a divergent telescoping series. It's entirely possible for that to happen. All right, now I want you guys to give this a try. Why did it become sine of 1 plus sine of 2? Because those were the terms that we had in the beginning that never had anything to cancel out with. So we have these guys. Yeah, just from the beginning. Oh, sorry, I should have underlined this whole thing. Yeah, all of this is going to not exist here. All right, let's do practice 2. And then it actually looks like it's the end for today. So these are some pretty short lessons here. Sometimes they combine this and the previous lesson together, but I think that would have been too long. So I'd rather have 2 short lessons than one jumbo one. Yeah. No, not necessarily. This one more. So we had a question. If the difference between these is 2 and they cancel out every other row, well, does that mean it will diverge? And the answer to that is no. It more depends on the type of function rather than how much they're separated by. And actually, this will be a good example for that. Let's take a look at n equals 1 to infinity of 2 over n squared plus 4n plus 3. So I want you to find the sum or state it diverges. Now you might be like, wait a minute, all of these other ones have had something minus something else for the canceling out. How is this going to be a telescoping series? And the answer is we need to turn it into a telescoping series. All right, and I was about to ask, oh, does anyone have the worksheet and know what the hint is? But I realized I only put up the worksheet like 2 minutes before class, so can't do that. My hint for this, use partial fractions. So this is what I was saying when I taught you guys partial fractions to begin with. Remember, partial fractions is an algebra technique. We don't need to be doing an integral if we're doing partial fractions. So try to use partial fractions on this to split it into 2 different things, and then you'll see that it's going to be telescoping. Is that a 4n or a 9n? It's a 4n. Seems like 5/6 is the dominant opinion. And coming up with the SN equation, how do I get the nth term again? You kind of look for the pattern and what's left over. So back in the sine example, like we stopped doing it in n equals 6, right? So the sine of 6 canceled out, and then we had a sine of 7 and sine of 8 left over. So it looks like our n value was 6. This was 1 bigger than our n and 2 bigger than our n. So that's how we ended up with, that's how we ended up with this up here. So once you stop, once you think you understand the pattern, look at what's left over and try to find a relationship. There's another minute or so. All right, let's take a look at this. So my hint is use partial fractions. Let's go ahead and use partial fractions on this. So what I'm going to do is I'm going to factor the bottom into n plus 1 times n plus 3. So that means I should be able to write this as a over n plus 1 plus b over n plus 3. All righty, so let's use cover up to get what these guys are, since it's just linear terms. So I plug in -1 to make this bottom 0. So I plug -1 into here, and I have 2 over 2. That's going to give me 1. Then for b, I plug -3 into here. That'll be -2. 2 over -2 will give me -1. So that means I can rewrite my series as the sum from 1 to infinity of 1 over n plus 1 minus 1 over n plus 3. All right. So now what we're going to do is we're going to start writing out the first few terms here until we see the pattern. So n equals 1. We have 1/2 minus a fourth. N equals 2. We have 1/3 minus 1/5. N equals 3. We have a fourth minus a sixth. Then we start to see our canceling. And as I predicted earlier, the gap between these is 2. So we should have to do one more than 2 or go 2 rows back in order to see our canceling here. All right, let's do n equals 4. We have a fifth minus a seventh. And we'll do n equals 5. So we have 1 over 6 minus 1 over 8. Like that. All right, so it seems like no matter what, this 1/2 and this 1/3 are going to be here. So I have 1/2 plus 1/3. And then let's see. So when I'm at n equals 5, I have a 7 and 8 left over. So I have 1 minus 1 over n plus 2 minus 1 over n plus 3. Because I was at 5 and I have a 7 and 8 left over here. So wherever I stop, I have 1 over n plus 2 and 1 over n plus 3. And then finally, if I look at the limit of this, so that's the limit as n goes to infinity of this, then both of these are going to go to 0 because we keep dividing by a larger and larger number here. So then we have 1/2 plus 1/3 is indeed going to be 5 over 6. So that's where that number comes from. All right. Does anyone have any questions on how we did this problem? Is this okay, the telescoping? All right. Well, that's actually, once again, that's all I have for today. I don't think we'll be finishing early on Monday, though. But these were relatively short. All right, guys. Well, I will see you guys on Monday where we will start learning some of these series tests. And these will be applied to series that we want to figure out whether they converge or diverge, but we don't really know how to sum them up directly like the ones today. So I'll see you guys on Monday.
I have
Professor?
a question.
Oh, sorry.
Yeah, what's your question?
How exactly can we define the telescoping series? I think I'm able to recognize it, but I wanted to jot down, I guess, kind of signs to look for just for my notes.
The main signs to look for a telescoping series is you have multiple copies of the same type of function with different n plus or minus a number inside. So for example, back here, we had sine of n minus sine of n plus 2. Here, after we did partial fractions, we were able to get it to look like that. So if you ever get it to look like where you have two similar functions with slightly different inputs, that's probably going to be telescope.
Okay, because then eventually you'll see the repetition, and then you'll be able to come up with the partial. Yeah.
Right. Yeah.
Okay.
Whatever the gap between these inputs are, that's how many times you need to go before you'll see that.
Okay. Thank you.
No problem.
Have a good weekend.
You too. I think there was someone else with a question.
Yeah, I had a question, Professor. I had a question about example 4.
All right.
It was like the one that, yeah, I'm not sure how you crossed out sine of n and sine of n plus 1.
Oh, so if I would have keep writing these back, in here I would have had a sine of n and then a sine of n minus 1 back in this column. So these would have crossed out with stuff that would be above there.
Okay, you just assume, like if you keep, because I wrote like sine of n minus 2 and I got sine of n minus 2 minus sine of n, and I didn't get to cancel out the sine of n minus 1.
Yeah, if you go far enough back in here, you'll be able to cancel out these things on the left here. If I were to write enough of them up here.
Okay, all right, thank you.
No problem. All right, guys. I will see you all on Monday.
Actually, I have one quick question. How did you come up with n plus n plus 2 and n minus n plus 3? Because I got n plus 3 minus n plus 4.
How did I get that?
Yeah.
So I stopped on n equals 5, right?
Mhm.
And what were the things I had left over? I had minus 1/7 and minus 1/8. So 7's going to be 2 bigger than my 5, and 8's going to be 3 bigger than my 5 that I stopped
Mm.
at. So that's how I got these.
Oh, okay. So it's 3 bigger, and that's wait. So
Yeah, so just
negative
whatever
4?
n you stop at, you compare the size of this to the size of whatever you have left over.
So, oh, okay. Thank you.
No problem.
Do you have time for